Thanks Reza and the Matroid team for having me here again at Scaled ML. I spoke at this conference, I don't know if it was the first year, but maybe it was one of the first years in 2017. So I was just looking back at my slides, and at that point, Apache Aero was a pretty new project. And so at that point, I was, desperate to find collaborators and people to contribute to the project. And so it's always nice when a bunch of time passes and you say, okay, like we've made progress. Like some things have changed and are better now. And it's always really hard to get a new open source project off the ground. But I've spent my career working on kind of what I called the boring part of machine learning and the boring part of data analysis. When I started working on the Pandas project, which was in 2008, if you can believe it, so it's been almost 12 years ago. So it's hard to believe that much time has passed, but I was really frustrated by very mundane data problems, and a lot of the work in projects like Pandas have actually been, certainly people doing machine learning are benefiting from having these more usable and accessible data manipulation tools, but they've also played a big role in liberating people from Excel. And so just being able to do, to essentially put a programming language that's accessible like Python in people's hands and a toolbox of things. Some members of my own family who are not educated in computer science started asking me about Python and Pandas, and so I'm like, oh, maybe this Python thing has grown a lot over the last decade. So currently, I operate a group called Ursa Labs, which is there's 7 of us. We're a non-for-profit development group focused squarely on the Apache Aero project. I worked on Pandas for about 5 years, but I haven't been involved in day-to-day Pandas development since 2013, which surprises a lot of people, but it has been fully a community-led and governed project since 2013. Since then, I've gotten involved in the ASF and in more big data related projects. Did a second edition of my book in 2017, and so that continues to be one of the standard textbooks for people learning about using Python for data analysis. So Ursa Labs started at the beginning of 2018 and has been an experiment in a new way of funding open source development. So I didn't want to start a company and raise money from VCs. I didn't want to do consulting, and I didn't want to work for Google. So I said, well, there must be a way that we can get a collection of interested parties together, people that have a strategic interest in the Aero project, and have them fund the work. And it's been really interesting in that, we now have, a couple of years of track record where a company, like NVIDIA can write us a check and we can immediately put that money into play, hiring people to work on the open source project. And I think one of the challenges in funding open source is sometimes a company will have budget, but they don't know how to actually put that budget into play. It's like, who's going to find somebody to do the work, who's going to pay them, who's going to manage their health insurance. So that's essentially the service that we're providing to our sponsors, that we'll look after the Aero project and we'll have a cohesive team of people working. And our studio has been, our studio just became a public benefit corporation. I don't know if any of you know that, but they've been really gracious in making this possible and putting in a lot of funding. So another 30-second aside is that it feels like there's not enough dialogue that happens across open source projects, particularly in the data space. So I've been thinking about this for the last 6 months, and I just set up a Discourse Forum, which you can look up and visit. And if you'd like to talk about topics like developer tools and other boring stuff that maybe you need to solve in your open source project, but you'd like to see what other experiences other people have had with that, I wanted to create some kind of a more neutral place that's not, a particular project's issue tracker on GitHub, which often has like a partisan feel, and people that aren't part of a single project's community often don't feel like they may engage less if it's like on, the Pandas issue tracker, for example. So I just started a thread there about continuous benchmarking. So always a topic that interests me. So the structure of this talk, I only have 24.5 minutes left, but briefly review the mission statement of Aero and what we've been working on for the last 4 years. Give you a brief shallow dive into the Aero columnar format and the binary protocol. Talk a little bit about some projects that have been using Aero and that have had success in recent years, and we'll tell you about what we're working on now, and my team in particular, and areas where you might look out for some Aero-related software coming to a data science library near you. So we started this project as a big collection of about a dozen or so open source projects, developers from those open source projects that recognized that there was a missing component, something to tie the room together. So there was no standard data representation for data frames or for tabular data sets that could be shared without serialization costs across data libraries. And the idea was very intellectually appealing to people, and many people reacted by saying, well, surely somebody has invented that and you're just not using it. And nobody had invented that, so we needed to get people together and build consensus to actually develop that. And so the mission of the project is to build open standards and build libraries to accelerate in-memory analytics and make things faster and simpler. I had a particular interest in working with people in the big data community because it felt to me that there wasn't a lot of cross-pollination happening, especially between the analytic database world and the data science and machine learning world. So there were a lot of computational problems in analytics, like things that to data scientists look like data frames, but to a database person, it's the internals of a SQL engine. And so a lot of really interesting development has either happened in open source database projects or in proprietary database land. And so for me, one of the goals of the project is to have an environment where database developers can collaborate with people building data science projects, and hopefully some interesting things will result. So I had the personal motivation of wanting to deal with interoperability issues that I experience, writing custom data connectors from one project to another. I'd also developed like an awareness of some of the fundamental computational issues in the internals of projects like Pandas. Certainly not unique to Pandas, but things like not having a very expansive set of built-in data types. Some of that's related to data representation. A lot of problems with memory use, and so I often tell people with Pandas you should try to have about 10 times as much RAM as the size of your data set. And so I'm sure many people in the room have run into the dreaded out-of-memory errors resulting from doing joins on large data frames, or even relatively innocuous operations that cause a data frame to be duplicated multiple times in memory. So at a high level, so the Aero project started out about building a language-independent, column-oriented data representation that could either be used on the internals of analytical query engines like databases, or in the internals of data frame libraries, so things like Pandas data frames. So that was the first thing that we built. We developed effectively a quote-unquote serialization protocol. We call it the binary protocol, that's used for communicating data sets between process address spaces and over things like TCP. So we'll talk a little bit about that. And to make these things useful, over the last 4 years, we've been creating a multilingual development platform that provides this batteries included experience for building data processing applications that use the Aero columnar format. So the particular problems that we want to deal with in the project that have vexed all of us for, certainly vexed me for most of my career. So number one is getting rid of serialization overhead when moving data from point A to point B. We want the way that the data is represented to be efficient for processing, both on modern CPUs and on GPUs. And hopefully in the course of doing this, we can make systems architecturally simpler by having fewer of these, having to maintain fewer data adapters, or having to worry less about what data structure is being used in each stage of a data processing pipeline. I have another goal, which is that I'm interested in finding ways for more open source developers to reuse each other's code. And so just looking at a Python developer versus an R developer, so historically there was no basis for collaboration between the average Python developer and the average R developer working on core computation for data frames, because fundamentally the data structure of a data frame is internally different in R versus in Python. So code that you write specific to R, you can't reuse that code. It has to be rewritten. And so that seemed to me like an anti-pattern. So hopefully we go from the left picture where we have to write a bunch of converters and everything's not very interoperable, to a world where if two systems speak Aero, they have a very straightforward way of plugging into each other. So over the last 4 years, we've been very busy. The project's developer community has been growing steadily. So recently, we crossed over 400 unique contributors. The main install path for the project is we aren't able to measure all of the package installs, but just in Python, the project was installed over 50 million times, via pip and conda. So when you include the reasons, I think one of the reasons for so many downloads is that the package has become a dependency of a number of products. Like, for example, a number of Google products pull in PyAero as a dependency. And we have some representation from 11 programming languages in the project. So, the relationship kind of at a code level between the Aero project and other data science projects. So we can use the things that we were building effectively to retrofit existing packages with faster I/O, and in some cases faster processing if there isn't that much serialization involved from converting from what data format they're currently using to the Aero format. I think the most interesting thing will be what does the next 10 years worth of new open source projects look like that are built from the ground up to be Aero native. I think that's the world that is, that's the ecosystem that is going to be the most interesting over the next decade or so. I've also observed that there have been a number of efforts to build effectively scalable data frame projects for Python and for other programming languages. And unfortunately, some of these projects haven't yielded a lot of investment in improving processing efficiency at the single node. And so some of the development that we're doing in Aero is oriented squarely at improving CPU cycle efficiency or GPU cycle efficiency, and not just throwing hardware at the problem to get scale. So very, very briefly, for people that haven't looked deeply at this, the Aero columnar format is intended as a companion to columnar storage like Parquet. Like, many people are familiar with Parquet files. Aero is where you put the data when you read the data off of disk, so it gets deserialized into memory in an Aero data structure. In database speak, it's called, the type of columnar that we use is called fully shredded, which means that when you have nested data, that the child components of the structures are contiguous and separate from the parent parts of the nested schema trees. If that makes sense, it makes sense when you make a diagram of it. But it's very efficient to process both in CPUs and GPUs. It's good for single-threaded, multi-threaded. We tried to satisfy a lot of different needs in designing the format, but it's a general purpose format. And to the extent possible, we've tried to be broadly useful for a wide gamut of data processing applications. So one thing that did drive some of the requirements in design was that we wanted it to be suitable both for workloads that involve a lot of random access and not only scans. And so sometimes database systems, they design their data structure solely around scan workloads where you read a table from start to end, but you may not need to necessarily pluck elements out of the middle of a table. And so we need to be able to have efficient I got it. Efficient random access into the middle of a table. The way that we message data sets between processes and between hosts, like over TCP, is using a binary protocol that we design where a data set is split into a collection of Aero protocol messages, which I will explain what's inside the protocol messages. But it's a streaming protocol, so if a sender and receiver don't know anything about the data set, the first thing that you would send them is the schema, and then you would send them essentially a sequence of chunks of the table, and then at some point you terminate the stream, and they have the entire data set then in memory. And so it's inherently based around streams and stream processing. And a table semantically consists of a collection of chunks, and so we're avoiding these kind of like massive allocations by splitting large tables into pieces. So the way that we serialize the data in these messages is there's a small amount of metadata that is in the first bytes of a payload that comes over the wire, and then that metadata describes the memory locations of each constituent column in that chunk of data. And so basically, the way that we avoid serialization is we look at the metadata and say, okay, I now know where all of the columns are located in the message body, and I just do pointer arithmetic and reconstruct the table data structure that references those pointer locations in the body. So so as soon as you have the message, there's you don't need to move or do any serialization after that point. So if you look at the internals of the message body, the memory that constitutes the table is laid out end to end according to the schema. So this is an example of a schema where we have an integer field and then a list of binary values. And if you extract all of the memory buffers from the schema, they create a sequence of end-to-end buffers that's deterministic and can be either shredded out and serialized or do pointer arithmetic and reconstructed in memory. We've tried to have a reasonably comprehensive set of built-in data types, solving some of the hard problems that end up taking up everyone's time, like what is a timestamp? Turns out to be, I don't know how many people have spent a lot of time talking about date and time types, but it seems to be a perennial source of effort, kind of the bike shed of data projects. But for applications that do need to embed their domain types into Aero data structures, we have a well-defined way of defining custom data types. And those are then the custom data types are represented using kind of the storage using one of the built-in types. So if you had latitude and longitude, you could represent that as a struct, and or you could it could be arbitrarily complicated. All right, so there's still a lot of work. Being a community project, we haven't solved all the problems under the sun, but if you're interested in data structure design and building these sorts of things, we'd love to hear from you. Some areas around building in encodings, particularly run length encoding into the format, has not been done yet. So if you have opinions about this, you know where to find us on the mailing list. So there have been a number of interesting projects that have been adopting Aero in the last few years. I'll tell you about a few of them. So many of you may know that NVIDIA has been building the Rapids project, which is a set of GPU-based data processing and machine learning tools. It is all the data internally in Rapids is, when it's a data frame, it's represented as Aero in the GPU. And so we have proof positive that Aero as a technology works well and as a CPU memory format as well as a GPU memory format. So it's been really great to see their success building this project. If we have Spark users, Aero is used to improve serialization speed, to get faster user-defined functions running inside PySpark. So if you're a Pandas user, you want to write Pandas native code. the pandas UDF user-defined function was created, and that's all powered by Aero under the hood. Database vendors have caught on that there's great value in improving the bandwidth of result sets to data frame users in Python and other languages. So last year, Google BigQuery shipped beta Aero support inside the Google Cloud BigQuery API, giving more than an order of magnitude speed up in getting data out of BigQuery into pandas. Snowflake Computing followed suit, doing exactly the same thing. And so I think that we will see, over the coming years, most modern database vendors build some level of Aero support into their clients and servers so that they can serve up large result sets to clients and get rid of all of the serialization, bottleneck. So, 30 minutes always goes by really quickly. All right. I'll try not to overwhelm you with detail, but I want to focus in on a couple of things that we have going on actively in the project. So if you look strictly just at C++ development, which is where I work in the project, there are many components to the platform. Can't go into all of these. Just building interfaces to storage formats is a great deal of work. We also have to worry about things like how do we deal with Amazon S3, and that's a whole pile of fun to make sure that works and is fast and robust. But there's a few specific things I want to talk about. So first is the datasets framework, and the second thing is computational code. So those are two of the active projects that my team is working on this year. So kind of the high-level idea there is that we want to have a consistent and easy-to-use API for accessing data that is stored in many different file formats and exposing that data in a way that can be queried, filtered, and processed efficiently. That's really kind of all there is to it. And so the way that we see the relationship between the datasets framework and the user is that we've been building this core data platform of memory management, data structures, and so forth. And so we scan the data out of where it's stored as efficiently as possible. That flows through kind of all of the core abstractions in the Aero library, and then can be processed in a number of different ways. So the computational code in the Aero project is the newest and most nascent part of the project. So if you are interested in implementing data frame type operations from the ground up in a new project, we'd love to hear from you and have more people involved in that. A kind of orthogonal part of the project, which I'm going to spend the next few minutes talking about while I have time left, is Aero Flight, which is an RPC framework for building data services that send and receive Aero data natively. So one of the ways that we're employing this in R is by under the hood translating dplyr expressions to the equivalent Aero primitives, and doing so without having any, the user can use dplyr as they currently do, and under the hood we translate everything to be the equivalent Aero computational primitives. So very quickly about Flight, some of you may have seen the blog post that we published announcing the project last year. We've actually been working on it for about a year and a half, but the idea is that gRPC as a technology for building services has become really popular. So we wanted to build a framework that would enable people to build data services that can send and receive Aero data sets that's built on top of gRPC, but without exposing the details of gRPC, so that you can just work with, okay, I have an Aero table, I have a server over there, I want to request a data set or send a data set, and for the low-level details of gRPC to be hidden from the user. And so a lot of the work there in dealing with gRPC is moving the data sets through the gRPC layers without incurring unnecessary data copies. And so I don't have time to go into the details of the demo, but you can pip install and run these demos now. But I have a simple flight server which is implemented in Python. The actions that it supports, you can send and receive data sets to the server. I'm running the server on my laptop here, and I will have a Martha Stewart moment where okay. So I have a large data set. The data set is 1.8 billion bytes. Let's see, how many megabytes is that? Gigabytes, it's 1.65 gigabytes. So I'm going to send the data set from a client to a server over TCP and see how long that takes. And so I'm able to move 1.65 gigabytes through TCP end to end in under a second. And then I can request the data back from the server in the same amount of time because it's using the exact same code on both ends. So I think it's pretty amazing to be able to move nearly 2 gigabytes or 1.5 to 2 gigabytes per second over TCP, and that's the kind of benefit that you get when you don't have any serialization overhead. So if you're building data services, you want to send and receive data faster, I encourage you to check out Flight. So some of the other kind of things that we care a lot about when we design this is that we wanted to support parallel get operations, so to not require all data to have to flow through some kind of a coordinator node. And so you can imagine if you are let's say a data services team supplying and making data available to a team of data scientists who are very hungry for data and requesting lots of data for doing analysis. So we wanted to enable people to use Flight to very naturally scale up a set of data services by adding new data nodes. And so if you go from 10 data nodes to 100 data nodes, when people make data requests, you can send their requests to different data nodes, that you don't end up with single bottlenecks and everyone going through the same coordinator nodes and then falling over when the level of data requests get too high. So I'll let you read about the details. So we've been very busy, and the project has gotten a lot bigger since the last time I was at ScaledML 3 years ago. But if you're interested in this domain and some of the boring computational parts of data preparation and analytics and data cleaning, we'd be really interested to hear from you. If you work with database vendors and they don't have Aero support in their clients somewhere on their roadmap, since you pay the money, you can generally ask them to take some of these things into consideration. So you can certainly help the open source project and the developers by encouraging encouraging your vendors to look at this and to get involved in the project. And since as I was saying in the beginning, I do think it would be valuable for more open source projects to talk with each other about technical topics that are relevant across projects, so not specific to a particular project, especially things like developer tools, continuous integration, benchmarking, and even some of the design issues that come up and that affect multiple projects. So I don't know if what I set up is the right place, but it's something that I would like to see happening more in the future. So if you have ideas about that and you want to chat with me about it, I'd love to talk more about it. So thanks again for having me.
Thank you, Wes. We have time for one question while we have the next speaker set up.
Right. The question was, is anyone working on integrations with Swift? Not that I know of, but I'm very interested in that. So I think two languages that haven't had representation that I'm interested in are Swift and Julia. So if you're a Swift developer or you know Swift developers who would be interested in this, very interested in that. Yeah. All right. Thank you.
All right, let's thank Wes one more time.